You've finally learned TR and TE, but right when you think you have it down, another massive question pops up. Why are there different MRI sequences? And why do radiographers sometimes choose spin echo instead of gradient echo? Well, let's dive right into this explainer and unlock what is honestly going to be one of the biggest breakthroughs you'll ever have in mastering MRI physics.
You've probably already put in the hard work, right? You understand the basics, you know your repetition time, your echo time. But then you're sitting at the scanner console wondering, wait, why do we need entirely different sequence families for different patients?
Stick with me, because by the end of this explainer, I promise you're going to perfectly understand the physical differences, the mechanics, and the practical, real-world uses of these two foundational sequences. You'll know exactly why they both exist and exactly when to use them.
Okay, let's do a super quick, under 1 minute recap just to set the stage. We know MRI relies on hydrogen protons in the body. We fire an RF excitation pulse to flip them into transverse magnetization so we can actually read their signal. But almost the second that pulse turns off, those protons start dephasing. They completely lose their synchronization. The TR is how often we repeat that pulse, and the TE is when we listen for the echo. And so, here is the absolute core of the issue. Because those protons dephase almost immediately, we desperately need a mechanism to rephase them and catch their signal before it completely vanishes. Spin echo and gradient echo are really just two different ways of forcing those protons back together to generate that MRI signal.
Section 1. Spin echo, the refocuser. Let's start with this first sequence family, which honestly serves as the reliable, gold standard baseline in MRI.
Think about the classic spin echo pulse sequence. It kicks off with a 90-degree RF pulse that tips the magnetization. But here's the absolute magic ingredient. Exactly halfway to our echo time, we send in a second, incredibly powerful 180-degree refocusing pulse.
To really picture this, imagine a track race. The 90-degree pulse, that's the starting gun. The runners, which are our protons, take off. Some are naturally faster, some are slower because of tiny magnetic field imperfections. So they start spreading out. But then the coach blows a whistle. That's our 180-degree pulse. It forces every single runner to instantly turn around and run back to the start line. Because the fast runners now have further to go, and the slow runners have a shorter distance, they all cross the finish line at the exact same moment. Boom! That is your perfectly timed echo.
And that track analogy brilliantly illustrates the physics happening inside the scanner. That 180-degree pulse literally mirrors the spins around the y-axis. By forcing them to physically flip, the spin echo sequence powerfully corrects for any local magnetic field imperfections. It's actively undoing the dephasing.
So the big takeaway here is that spin echo gives you absolutely gorgeous, excellent image quality. It gives you true T2 weighting and is incredibly robust against artifacts. But you pay a pretty steep price for all those 180-degree pulses. They take a lot of time to apply, which means spin echo sequences have noticeably longer scan times. Section 2. Gradient echo, the speedster. Now that we understand the reliable baseline, let's meet the rebel speedster of the MRI world.
If you map out a gradient echo, do you notice what's glaringly missing? There is absolutely no 180-degree refocusing pulse. None. Nada. Instead, we use something called a gradient polarity reversal to create the echo. We apply a gradient in one direction to intentionally dephase the spins, and then we rapidly reverse the gradient to rephase them.
Going back to our track race analogy, it works kind of like this. We use a smaller starting gun, a flip angle that's often less than 90 degrees. The runners start spreading out again. But instead of a coach stopping them and turning everyone around, we basically just tilt the track downhill and then violently tilt it back uphill using magnetic gradients. This physical tilt forces them back together incredibly fast.
Since we're not sitting around waiting for a 180-degree RF pulse to do its job, gradient echo allows for incredibly fast image acquisition. Shorter TR, shorter TE. But, and it's a big but, because it doesn't actually flip the spins, it cannot correct for local magnetic field imperfections. It's highly sensitive to its environment, making it incredibly prone to susceptibility artifacts from things like iron or air tissue borders.
Section 3. The ultimate showdown. Spin echo versus gradient echo. Let's put these two head-to-head to really solidify your mental framework. Think of this as your ultimate cheat sheet for your exams and your daily practice. Spin echo rephases with an RF pulse, making it slower, but giving you that gold standard, artifact-resistant, true T2 image. Gradient echo rephases using gradients, making it lightning fast, but it produces T2 star-weighted images, which are way more sensitive to artifacts. Section 4. When do we use each? Let's take all this physics knowledge and apply it to your actual real-world workflow at the console. Spin echo is your absolute go-to when exquisite anatomical detail is just non-negotiable. You can use it heavily in brain imaging, spine imaging, and musculoskeletal MRI. Also, fun fact, because flowing blood completely moves out of the slice before that 180-degree pulse can even hit it, the blood appears pitch black. This creates a dark blood effect that's absolutely perfect for looking at the walls of blood vessels.
On the flip side, you grab gradient echo when speed is paramount. Need a super fast breath hold scan of the abdomen? GRE is your best friend. But get this, we also use it when we actually want to exploit its weakness. Because it's so sensitive to magnetic field distortions, it's brilliant for detecting the iron in blood products, making it perfect for finding tiny microhemorrhages.
Now I want to bridge this into something that will really make you stand out as an advanced thinker in the MRI suite. Cardiac MRI. The heart is literally always beating, which means speed is everything here.
When we compare the two results side by side, spin echo gives us that dark blood signal void because the blood flows away. But on the gradient echo side, we have a specialized sequence called Balanced Steady-State-Free Precession, or BSFP. Because gradient echo is lightning fast and uses a continuous inflow of relaxed spins, the blood appears brilliantly bright against the darker heart muscle. That bright blood contrast is exactly why gradient echo variants rule the world of cardiac cine imaging.
Section 5. Memory tricks and common confusions. Before we wrap up this explainer, let's clear up some beginner confusion and give you a really sticky memory toolkit.
If you ever freeze up during an exam, just fall back on these nicknames. Spin echo is the refocuser. Why? Because it literally uses a 180-degree RF pulse to refocus the protons, fixing the image and eliminating imperfections. Gradient echo? That's the speedster. Skipping that 180-degree pulse makes it insanely fast, but leaves it highly sensitive to every little bump in the magnetic field.
Now, a question I hear all the time is, wait, do all the dozens of crazy sequence acronyms on the scanner actually belong to these two families? And honestly, yes. Almost every sequence you run, whether it's a fast spin echo or a rapid BSSFP cardiac scan, is fundamentally just a derivative built on top of these two parent families.
If you've wrapped your head around how the refocuser and the speedster operate, you have literally just unlocked a massive piece of MRI physics today. Understanding this completely transforms how you look at the scanner console. I really hope this explainer made things clear for you. What MRI physics topic still trips you up? Let us know in the comments below, and make sure to subscribe so you don't miss our future explainers. Thanks for learning with us.